Time we're doing one of our wonky coins, and then what I said to do this time was go over how to make this algorithm that we wrote more efficient, right? And so if you remember, essentially what we're doing is we're sending back any number, right, that is not equal to 0 back into the wonky coin machines, and until that number equals 0, we're going to add it all the zeros up at the end, okay? Make a big tree. So it's going to look like this, right? So let's give a visual representation of this. If wonky coins is equal to 5, then that means it's going to be wonky coins it's going to be 5 over 2, and then 5 over 3, right? And then 5 over 4, 5 over 4. Okay? Now, of wonky coins of 5 over 2, this is actually 1. This is a 2, and 3 is 1, and then this is 1. Okay? And then 1, as we did last time, is equal to 3 zeros, right? And then 1 here is also equal to 3 zeros. Boom, boom, boom. And then 2 right here, what this is equal to is it's going to be 2 over 2, and then 2 over 3, and then 2 over 4, right? And then 2 over 2, this is going to be 1, and then 2 over 3, this is going to be equal to 0, and then 2 over 4, this is also going to be equal to 0. And here we go. And then this is 1, remember 1, we have 3 again. Boom, boom, boom. Okay, so you add that up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have a total of 11 zeros here. Ooh, 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 ooh. Right, but if you notice what's going on here, and it's inefficient, is that we're doing a lot of duplicate work. See how many times we have 1 here of 1, 2, 3 times. I mean, every time we have to calculate that, okay? The same thing, yeah, so if we have 3, we have 1 3 times, okay? And the higher you get up, you'll the same thing with 2. 2 will be more and more the higher the numbers are, okay? So there's a way that we can keep on saving, right? So what we know that, for example, 2, right, has 1, 2, 3, 4, 5. So once this right here calls on 2, we can just send 5 to it automatically, and the same thing with 1. If we could do that, we could save ourselves a lot of time. Essentially what we're going to do is we're just going to add a way of remembering those numbers that were in the past, okay? So for Ruby, we're going to use a cache. And for the cache, we're going to equal it to an empty array, okay? So we keep this the same, right? If n equals 0, it's going to return 1. But also, else if, boom, 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 it's in, so if it's in, if we remember it, right? If we remember cache of n, right, with that number, then we're going to return cache of n. Okay, return the elements. So we're accessing, so the index of that number, going to be there, we'll return what number is at that index, right? Else, we're going to set, if we don't know the number, we're going to make a new number, cache of this new number n, equal to this right here. Right? So this way, we're saving up all this information right here, and we can return numbers way, way faster. Okay? And it's hard to tell with this, but once numbers get really, really big, significantly bigger, it'll make the algorithm move a lot faster and be a lot more efficient. I think before the algorithm was big O was exponential, right? And then this one will be, I think, linear.